All right, we're going to look at this example 4.8 in Unit 4, problem set 4. Okay, we need two concepts from probability. One is total probability, and the other one is Bayes' formula. So let's first review these two concepts a little bit. Okay, so it has to do with conditional probability. So let me first review a little bit about conditional probability. So imagine we have two events. So A and B, these are two events. Okay, and we say they are events, so they belong to certain probability space. And probability that given B, what is the probability A, is the probability of A and B divided by probability B. So this is the definition of the conditional probability. It simply means the following. The easiest way is to look at the Venn diagram. This is omega over here, and we have A over here, and we have B over here, right? And in the middle over here, this is A intersect B. So if we know B has happened, and what is the probability that A has also happened, we use this overlap and divide it by the probability of B. That's a conditional probability. Okay. So the most useful formula or the construction of the probability tree is the following. So it involves usually two events. So still two events. Let's say we know that for probability A, for event A, the probability is P, okay? And then event A doesn't happen. This C means event A doesn't happen. The probability is going to be 1 minus P. Okay, so these two. And imagine we know two conditional probabilities. So on these branches, we have conditional probabilities. The first one says, if A happens, what's the probability B happen? And this is the probability. Okay. And of course, we have the other one. If A happens, what's the probability B doesn't happen? And again, if you add them up, should it be 1? So usually we just need to know one of them, and then we will know two. And for the second branch, we also have, say, suppose A doesn't happen, what is the probability B can happen? And this is the conditional probability. And this is the most useful so-called probability tree diagram. It looks like a tree. Okay. If we know this information, really we just need to know the following. Probability of A, and then probability of A. After A is given, what's the probability of B? So these two we need to know. And for the second one, we already know 1 minus P, so we just need to know if A doesn't happen, what's the probability B actually is going to happen. So we need really just three pieces of information for this tree to be complete. But based on this tree, we can actually do the following thing. This is called the total probability formula. We can, based on this tree, we can find the probability of B. And how to do that? Probability of B is going to be simply the sum of products along all branches leading to B. It's easy to understand this one. Suppose you want to know what's the probability for B to happen, then you just need to look at two situations. One, what if A happens? And then you have this branch over here. If A happens, then you have this one. And the second one is over here. So we look at two branches leading to B. And then we know the probability for B to happen is going to be probability of A times probability of given A, B over here, and plus the probability of A doesn't happen, and the conditional probability. Okay? Or using the total probability formula, we can actually see what this one is. This one over here is exactly the probability of A intersect B. And the second one over here is the probability A complement intersect B. So for B to happen, it's either A happens or A doesn't happen, and that's what we have. Okay. And for the Bayes formula, we need to find a conditional probability. Let me move to the side over here to illustrate this one. Suppose we still know this probability tree, and we want to find the following probability. Suppose we know that now B has happened. What's the probability of A? And if you look at the tree, it doesn't give us this information. But on the other hand, we can use the Bayes formula, use the total probability formula to find it. And this one over here is equal to, of course, it's going to be probability of B at the bottom according to the conditional probability formula. And on the top, we have probability of A intersect B. And then we look at what we have on the left-hand side. And this part over here is the sum of products along all branches leading to B. Okay? And on the top, we just have the product of that branch, just one branch, starting from A. So what we have over here is the same denominator. We have a big denominator. It's kind of tedious to write down. The easiest one is just to look at the diagram. So we're going to have the sum of these two branches marked red. And then we look at which branch is coming from A, and it's this one. Okay. So what we have over here is the following denominator. So we have the sum of two branches, probability A and probability A doesn't happen. And then on the top, you have probability of A and times the probability B of A. So what it means is that suppose we have this probability tree. We know these conditional probabilities. And now we know B has happened. What is the possibility because A has happened? Because we know for B to happen, either A or A complement has to happen. Now we are asking the question, suppose we know B has happened. And what is the probability that actually it is from the cause A? All right, I hope that's enough review, and then we're going to look at example 4.8. We're going to just use intuitive approach, but we remember these two formulas, and if it's necessary, we're going to construct the probability tree. Okay, so let's look at this problem. Imagine that after many times of rolling his dice, Dr. Jian suspected that one of his two dice was not a fair die. It seemed to him that the die favored the bigger numbers. He set out to try. He rolled the suspected die 3 times, and he got 4, 5, and 6. Question: if the die is fair, what is the probability that for 3 times in a row, the number showed on the top is greater than 3? And here we are going to assume we have really just 2 events, 4, 5, 6. This is considered 1, bigger numbers. And the other one is 1, 2, 3, like this. So this is A, and this is A doesn't happen. Okay, so we're going to try to look at the probabilities. If it's fair, say, assume it's fair, then this one is going to be 0.5, this one is going to be 0.5. This is assignment of probability. So we have this one over here. we say if the die is fair, and that's what we have. Okay. Now, so if the die is fair, if we roll the die once, we have 50% chance to get either 4 or 5 or 6, and 50% chance to get 1, 2, 3, these smaller numbers. And we assume these 3 rolls are independent. So the probability over here, based on independence, we can say that assuming independence, we have of these rollings, of 3 rollings, we should have the following thing. We have the probability to get 4, 5, 6 for the first row is 0.5, and for the second one, 0.5, and for the third one is 0.5. So this is 1/3 to the third. This is what we have. Okay. All right. So this is really about independence. We sometimes call the multiplication principle. And now we are going to look at how to formulate and solve probability problems using a probability tree. Okay. Now we are going to get another event involved over here. So now we have an insider, and this insider is telling Dr. Jiang that the die actually is unfair. Not only he knew the die is unfair, actually he knew the die favors the bigger numbers, 4, 5, 6 to 1, 2, 3 by 2 to 1. Okay. So what does that mean? So this is insider's view. According to the insider, this die is unfair, but unfair in a very specific way. That if you look at event A, that's 4, 5, 6, and he was saying that this is 2/3. Okay, the probability, that's P. And a complement, that's 1, 2, 3, and that's 1 minus P, and that's 1/3. So that's the situation if the die is unfair. Okay. Now, after rolling the die 3 times, Dr. Jiang got 4, 5, 6. Now, this seems that this die is really unfair. But on the other hand, we know that small probability events can happen. So this die can still be fair. So how can we use this information somehow to look at the problem to see if we can actually believe in this insider? And the important thing over here is that we have to have some kind of initial assumption about this insider. So the initial so-called belief is needed. So if you read on, we have the following problem. So with what confidence probability should Dr. Jiang believe this insider, assuming that his initial belief in this complete stranger is only 20%. So this one over here means the following thing. Its interpretation is thus, that initially Dr. Jiang thinks that because he believes only with 20%, 0.2, that in this belief, in this insider. So with 0.2 probability, he thinks this one over here is unfair. And that's how we interpret this initial belief. And for 0.8, he would think that still is fair. Okay. And then we are going to construct the probability tree. And then we have the following thing. If fair, that's A over here, and this is B, or this is A complement. Okay. If it's fair, then what is the probability that we are going to get 4, 5, 6 3 times if it's fair? That's what we exactly actually calculate. B over here is that 3 times we get 4, 5, or 6. That's the probability is, we know it's 1/2 cubed, right? And that's the one we have. And we don't need the other branch because we know that. What's the probability that if it's fair, we don't get 4, 5, 6 3 times? And that's going to be 1 minus 1/3, 1/2 to the third. Okay. Let's look at what if it's unfair. Unfair, that means we're going to have on this event 4, 5, 6, we will have 2/3 probability. And the other 3 dots, 1, 2, 3 cases, we have 1/3. So given that this die is unfair, and what's the probability we can get B over here? And that's going to be 2/3 cubed. Okay, 2/3 cubed. So now what do we want to do? This is what we want to find. Suppose now we have B has happened. That means for 3 times we get bigger numbers. What is the probability that this die is still fair? That means we're going to try to find this one over here. And that will give us the probability that we will actually, Dr. Chen will trust the insider. But really, what we want to find is if B has happened, what is the probability that this die actually is unfair? So we really want to find this AC, this branch. So now let's apply the Bayes formula. So we're going to look at the branches leading to B. So what we have over here is this branch. Okay? And then we have this branch over here. The other branch is missing, but it's not actually it's not really useful. So according to the Bayes formula, this is what we have. If we want to find out the conditional probability that B has happened, what is the possibility that AC has happened? Then we look at this. In the bottom, in the denominator, we have the products along 2 branches. So first branch is 0.8 times 1/2 cubed. So that's the one. The second branch, we have 0.2 times 2/3 cubed. Okay. And on the top, we look at that branch coming from AC. So the 0.2 times 2/3 and cubed. So that's what we have. And if we simplify this and use a calculator, it's going to be faster. But I believe the answer is about 0.39. So the interpretation is this. Initially, Dr. Chen believes with only 0.2 probability that this die is unfair. But after 3 rollings, and he was getting 4 or 5 or 6 for 3 times, and then his belief in this unfairness for this die has increased from 0.2 to 0.39.